All right, this is Mr. Peterson with another screencast for AP Environmental Science. Today, we're learning more about climate change. Of all the things we are concerned about in environmental science, climate change is one of the biggest concerns because it has the potential to affect life everywhere on Earth for long periods of time into the future. Now, climate change is nothing new for the Earth because it has changed many times. It has been hotter than this is now, and it's been much, much cooler than it is now. It's been cooled by volcanic ash and meteor impacts, and it has been warmed by the changes in sun output. Cooler periods, commonly called ice ages, are called glacial periods, and the warmer times in between are called interglacial periods. Now, the movies make it seem like ice ages are when the entire Earth is covered in ice, but it's really a little more subtle. Ice ages are when the average temperature of the Earth is a few degrees cooler, allowing the ice at the north and south poles to grow, and glaciers can expand towards the equator. But by no means do they ever cover the entire globe. Now, we've been fortunate that for the last 10,000 years or so, we've had a relatively stable climate. That has allowed human civilizations to flourish. As human civilizations have progressed, though, the average temperature of Earth has been increasing for the past century, and that's alarming for many reasons, and we're going to learn about that today. Now, the question that always gets asked here is, how do scientists even know what the Earth's temperature was past about 150 years ago when modern records started being kept? The answer lies in lots of places, but one of the easiest to understand is ice cores. As snow falls on the polar regions of the world, most of that snow doesn't melt. It simply builds up on top of the last year's snow, and gradually the snow on the bottom gets packed down to form ice. Repeat the process over thousands of years, and you've got a glacier that's thousands of feet thick. That's when this guy comes in. This is an ice core drill, and it's used to drill down into the ice to extract chunks of ice, which then get pulled up, and they look like this. This and each layer you can see in the core is from a different year's worth of snow. So, by starting at the top and counting down, the deeper you go, the older the ice. It's beyond the scope of this class, however, to determining the historical temperature works, but suffice it to say that there are unchanging laws of nature that affect the ice formation that vary by temperature. So, by looking at each year's ice layer, one can work backwards and come up with a fairly accurate estimate or assessment of global climate during periods of time before modern weather records were kept. And then by looking at ice cores from all over the world, these individual measurements can be confirmed from multiple locations, which adds to their credibility. There are several other lines of evidence that can be used, such as tree growth rings and layers of pollen that settle at the bottom of lakes. Now, I'd like to state the obvious at this point. None of us were there, so we don't know with 100% accuracy what the global temperature 3,500 years ago was. But the power of science is that it lets us make a very good estimate of it. It's easiest to see with dots. So in science, we perform an experiment and it gives us evidence. And then we perform more experiments, it gives us more evidence. And then we can connect the dots of evidence and come up with a theory. But there can be competing theories to explain the evidence. As we gather more evidence, we can eliminate the incorrect theories. And all theories make assumptions based off what we know. But those that make fewer assumptions are more likely to be true. So we tend to focus on the theory with the fewest assumptions. This allows us to get an accurate picture as we can. So our theory versus the truth. It may not be completely accurate, but it's pretty close, and we can use it to basically explain things. Now, to flash back a bit, there's an important concept that we learned a long time ago, and it's that the natural greenhouse effect. Incoming light from the sun strikes the Earth, and when it does, it's converted to larger wavelength infrared radiation, which is mostly heat. As that heat moves back towards space, it interacts with greenhouse gases like water vapor, carbon dioxide, methane, and nitrous oxide. As it vibrates those molecules, they re-emit even larger wavelengths of infrared radiation, which warms the lower parts of the Earth's atmosphere. This is completely natural, and without the greenhouse effect, life on Earth wouldn't exist. Even on the coldest night of winter, when it might be 15 degrees in Thomasville, you can still thank the greenhouse effect for keeping the Earth warm, because without it, it would be around minus 250 degrees Fahrenheit, like the dark side of the moon. The problem is that the warming climate over the past 100 years is linked to the increase in greenhouse gas emissions, most notably carbon dioxide. Ever since we started burning fossil fuels and cutting down trees, global CO2 levels have been on the rise. What's worse is that the same sources for global temperature, like ice cores, contain trapped bubbles of air that can be analyzed to see what CO2 levels were back in the day. The bad news is that periods of higher CO2 concentration in the atmosphere are linked with periods of higher global temperatures. So, it's not like Earth hasn't seen this before. The problem is that the levels of CO2 we're putting in now and projected for the future are higher than anything the Earth has ever seen. Methane and nitrogen oxides are also increasing due to human activities, and they also trap heat in the atmosphere. There have been several noticeable effects of warming over the past century, as Arctic temperatures have warmed twice as fast as average temperatures in the rest of the world. This picture, taken in 1948, is only recognizable in 2004 when you look at the mountains. The glacier that was here was melted, retreating back into the mountains. The scene, repeated all over the world, has led to an increase in sea levels over the past 100 years of about 6 inches. So far, global average temperatures have only gone up about 2 degrees in the past century. But as the levels of greenhouse gases rise, temperatures are projected to increase even more. There are several factors that may yet affect global warming, and it's tough to figure out exactly what's going to happen because you're dealing with an experiment that is the size of Earth. For example, oceans play a very important role in moderating Earth's climate. As it takes a great deal of energy to warm water, the oceans buffer the rest of the Earth from quick changes in temperature, and they also absorb carbon dioxide from the air and store it in mineral deposits that can be stored in ocean sediments for thousands of years. That's great for us, but studies are beginning to show that as the ocean begins to warm, the carbon dioxide is less soluble in warmer water, so it comes out of solution just like the bubbles in the can of Coke. If warming is caused by increased levels of CO2 and warming water releases more CO2, guess where that leads? Positive feedback, where a small change brings a bigger change, which repeats to bring an even bigger change, and it goes on and on. Remember, positive doesn't mean it's good. Positive means that the change that starts is going to grow in size. And cloud cover is another big unknown. Warmer temperatures cause evaporation, which makes more clouds. Clouds are light-colored and tend to reflect the sun's light back out of the atmosphere, which could slow the Earth's warming as a result. However, an increase in thin, high-altitude clouds could let sunlight in, but trap heat. After all, water vapor is a greenhouse gas, too. At any rate, it's not something we can count on saving us in the end. Air pollution is another big unknown. It's a well-known phenomenon that when large volcanoes erupt and throw up clouds of sulfur dioxide ash, that the ash cloud can be dispersed over the Earth and actually shade out the Earth by reflecting incoming solar radiation. That can cool the Earth. Soot, an air pollutant that is produced by burning of carbon-containing materials, can have a similar effect. So, that may cancel out some of the warming, but it's hard to predict. And there's less of kind of pollution being produced as countries reduce it for human health reasons. Additionally, volcanoes throw up large amounts of carbon dioxide, and that's actually a greenhouse gas. So, again, these aren't things that we can rely on to prevent global climate change. So, what are the possible effects of warmer atmosphere? Well, first up, we need to clarify something. Whenever someone says on a bitter cold day in January or an abnormal cold day in May, so much for global warming, it's adding to global warming because it's just a bunch of hot air. Any strange weather event on a local scale is just the local weather. Weather happens on a day-to-day basis, and it turns into climate when weather measurements are averaged together over long periods of time, usually at least 2 to 3 decades at a time. So global climate isn't affected much by one hot day or one cold day. It's the average that counts here. In the past, global climate has changed many times, but usually the record shows that it has changed gradually, over a period of time that stretches over thousands of years. The trouble here is that we are facing a rapid increase in the Earth's average temperature over a short period of time, mainly in this century. There's another old idea here of tipping point. Push a natural system like this rock for a while and you may see no noticeable change, but push it hard enough and a sudden change can be released that will be rather difficult to undo. Climate change is like that, and I'll mention a few ways that tipping points could affect us as we run through the key problems of global climate change. First up is drought. Initially, it seems like warmer temperatures would increase evaporation, which would lead to more rainfall. But it's not that simple. It may increase evaporation, but the eventual precipitation may not fall back on that area. Drought conditions are projected to increase, and this has the potential to amplify global warming through positive feedback. As more areas of vegetation dry up and stop doing photosynthesis, then less CO2 will be absorbed from the air, which then results in more warming. And then we have areas of the world that are normally covered with ice and snow may begin to melt. This one is particularly sneaky because the white covering of the Earth's surface helps reflect light without allowing it to become heat energy. So when temperatures warm and the ice melts, the darker colored ground underneath doesn't reflect light. It absorbs it and converts it to heat. So it's a tipping point again because a small amount of warming causes ice to melt, which causes further warming, which melts more ice, and so on. And the melting of ice and snow on ground leads to changes in sea levels as the water flows into the ocean. Plus, when water warms up, it expands, so it takes up more room than when it's cooled. With current and projected changes, it's very certain that the average sea level will rise about 1 to 2 feet during the next century. The red lines in the map shows the area that will be submerged with a 1 meter rise, and a foot is about 1/3 of a meter. It may not impact us greatly on the Gulf Coast, but I think the entire eastern coast of Florida is going to be pretty upset about the whole thing. Not to mention all of Miami. And then you have changes in permafrost. Permafrost is the frozen layer of soil that lies about 1 foot or so underground in the tundra and a few other biomes. In the summer, the soil thaws down to the layer of permafrost, but the entire thing freezes over again the next winter. Permafrost is important because there's a lot of methane frozen into the soil. It's another tipping point because the world warms enough to melt the permafrost, and the amount of methane that would be released would be staggering, and since the methane is a greenhouse gas, that's going to help things get warmer, melting more permafrost. And then you have ocean currents, and they're important because they circulate nutrients in the ocean and moderate climates of the continents that they flow near. The currents are caused by differences in the temperature and salinity of different areas of the ocean, and so as global climate change alters the temperature and rainfall patterns, these currents have the potential to change as well. These ocean currents play very large roles in setting up temperature and precipitation patterns as well, so changing them could change the weather of nearby lands. Extreme weather events become more likely under global climate change. That may mean more heat waves or stronger storms because the atmosphere is warmer and can hold more moisture. One of the factors that determines how strong a hurricane will grow to be is the temperature of the ocean underneath it, and the warmer that is, the stronger the storm can be. Next up is the effects on biodiversity. Simply put, all organisms have a range of tolerance that can withstand for temperatures and rainfall, and if those ranges are exceeded, species can either migrate or go extinct. You might not think that plants can migrate, but they do when they produce seeds that travel to a new location and start growing. Species with a wider range of tolerance that we think of as generalists will do well, like cockroaches. But specialist species that have trouble hanging on, many of these species provide us with useful ecosystem services. And adding insult to injury, if a particular species is able to withstand the coming changes directly, what happens to their food chain and ecosystems around them if other species can't tolerate the new conditions? So global climate change will also change the areas of the world that are currently suitable for agriculture. Areas of the world that are currently deserts may receive more rainfall and become suitable for agriculture, but areas like the U.S. Midwest could dry up, rendering them unsuitable for large-scale agriculture. That one hurts a lot because food production is one of the first things on the list for a country's own security. And then you have human health, and it's going to be affected. So as temperatures and rainfall patterns change and the tropics expand, new areas of the world may be exposed to infectious diseases and parasites. People still die in this world during heat waves, and that's only going to increase as temperatures get warmer. Many forms of air pollution, like smog, which can make us sick, increase in warmer temperatures as well. So what's to be done? The world is slowly coming around to the fact that this one is the most serious issue that humanity faces in the long term. That doesn't make it easy to deal with, though. It's hard to deal with because the causes of the issues are global, and so are the effects. Working together with other countries is a hard thing to do. Second, the effects are long-term. They are mainly important issues that face us today, like poverty, starvation, disease, and war, and we tend to focus on those. It's always easier to feel good about doing something that affects the here and now than it is to focus on something where the effects won't be fully known for decades. Politicians, who have to get reelected every 2, 4, 6 years, tend to get reelected more by focusing on the short-term issues. Next to last, it's hard to know exactly what changes will take place over the next century with this issue. So it's hard to motivate people in countries to make if you can't specifically prove what's going to happen in any particular area with 100% certainty. It's a certainty that much of this will come to pass if changes aren't made, but pinning each effect down to a specific area is tough to do. And last, many of the changes that will have to take place are unpopular because they will cause some disruptions to lifestyles and economies. I like this cartoon, though, because the result of making the changes will be beneficial in many areas, and the cost of not doing anything is too much to bear. So what are the options? There are lots of strategies, but they fall into 2 big categories. Input or prevention strategies focus on keeping greenhouse gases out of the atmosphere by preventing their release. That may include moving away from fossil fuels, reducing deforestation because plants absorb CO2, and slowing population growth because fewer people on Earth would mean less resources. used, so less CO2 production. Output strategies focus on cleaning up the damage that's already occurred, and the big one in this category is the idea of carbon capture and storage. Basically, it means that as CO2 is produced in factory and power plant exhaust, it can be captured and dumped underground and stored, thereby preventing its release into the air. It's possible this would work, but there's three main problems. One, the technology costs money, so that raises the cost of power for everyone. Second, what happens if it leaks back out? And third, it at best gives us an extension on our global homework, because the fossil fuels will run out someday, so it might be better to go ahead and bite the bullet, start focusing on renewable sources of energy that avoid CO2 entirely. And then there are some crazy ideas, the what ifs, and they're called geoengineering. If you remember that sulfur dioxide from volcanoes has caused short periods of global cooling, some people are proposing sending balloons full of the stuff up into the atmosphere, where the sulfur dioxide will be released, and that will reflect the sun's light and cool the earth somewhat. There are lots of other crazy ideas, some of which may actually be useful. There are two major problems with these, though. The number one is the scale that's required in order to be effective. Second, perhaps more important, is what I call the Law of Unintended Consequences. Some of these are great ideas, but they could have unforeseen effects that might be more damaging than the original problem they set out to solve. So that brings me back to the cartoon. If we know all of this is going on and we need to deal with it, how much is that going to cost? Current estimates are that it would require halting global warming in the next few decades would require something around 3% of the gross domestic product of all the countries of the world. That is an enormous amount of money. Most of the world acknowledges that it would be in the long-term best interest of the world, because even the medium-level outcomes of global climate change are too much to handle and would be far more expensive to deal with. The problem remains, though, that it's a long-term problem, and there are many short-term problems here today that we tend to focus on. And although we like to trash the government for just about everything, it is one of the roles of government to protect our long-term interests and the environment, science, commons. So government has a role to play here. One of the ways that government can help is to regulate carbon dioxide and methane, the two biggest greenhouse gases, as pollutants. That means making laws to address the emissions of both these greenhouse gases. It's just one part of the picture, but if those gases are regulated, then they can be taxed. Countries will still need the same amount of money to run themselves, but if we choose to tax individual paychecks less and tax carbon production more, lots of people would do everything they could to get out of paying that tax. And if the environment benefits, great. Just think of how hard people work to get out of paying their income taxes. Finding ways to avoid paying carbon tax would be just as popular, because nobody enjoys paying taxes. Another strategy is called cap and trade. In the cap part, a limit gets placed on how much human-generated greenhouse gases can be produced. Companies and other large polluters get permits to emit those pollutants, but if they can find ways to reduce their own emissions, then they can trade their permits for money to other polluters who haven't gotten their act together yet. In the end, less pollution takes place because the cost of emitting carbon becomes more expensive, so alternatives become more appealing. There's a lot of problems with this one, mostly because there are so many sources of carbon pollution out there, and the government hasn't proven itself to be terribly effective at most forms of regulation. Another way for government to have an effect is to level the economic playing field. Currently, the government subsidizes many forms of fossil fuel energy production. Switching those subsidies and tax breaks over to renewable carbon-free sources of energy would go a long way to cutting carbon production. Again, businesses and companies will usually jump in line with most things that help their economic bottom line, especially as consumers start to demand more and more of this type of action. Also, governments can help other countries leapfrog over some of the dirtier parts of development by giving them technology. These solar panels on the roof in a third world country were donated by richer countries, and it helps cut emissions in those countries. Many of the countries that are the worst polluters are too poor to do anything about it, so countries that are economically better off have a role to play by helping them catch up environmentally. The effects of global climate change are global, so it's everyone's interest to help. Last, governments can enter the treaties with each other and agree to certain regulations on a global scale to help reduce global climate change. The Kyoto Protocol that started in 1997 was a major step towards that, as many countries agreed to reduce their carbon emissions over the next few decades. The U.S. never joined that over concerns for the harm the economy would suffer from it. All about the money. Now, industries has their role to play as well, and we can lump large organizations like universities and schools into this as well. As the cost of energy continues to rise, many industries are jumping into the green bandwagon, not because they want to be green, but because they have a vested interest in sticking around for the future, and anything that can be done to ensure that while cutting costs at the same time is a win-win situation. So, industries that lag behind may see themselves cut out of the marketplace as other companies spring up that can do the same job, but for a less cost, and appeal to the public demand for green solutions. So, since it's pretty certain that some effects of climate change are unavoidable at this point, What can be done to prepare for it? Even cutting emissions by 50% at this point would still lead to some changes, so it's best to take a two-pronged approach. Fix the underlying problem, but take precautions for the future as well. And as sea levels rise, building seawalls will become more important for low-lying areas. Building codes in these areas may need to be changed to ensure that new construction will place buildings high enough to escape higher storm surges. Public cooling centers will have to be established. These already exist in large cities, and they serve people who can't afford to run an air conditioner and would otherwise die from heat. In the future, these spots will become more popular. Cities also need to make plans for the water supply, as future changes in rainfall patterns could alter the existing supplies used today.